Hey, welcome back, class. This video, we're going to take a look at limiting and excess reactants. This works with any reaction that you can think of that I'm going to throw at you in class or in lab. So let's just jump in and let's see what we have. All right, so we've got a little background information. We got rocket engines using what's hydrazine, which is a compound of nitrogen, and hydrogen peroxide as a propellant. So when these two reagents come together, it generates a reaction that we can trap the pressure and a lot of the energy that's from this that we can use as a propellant. So that's what that means, as a propellant, right? Particularly like for space aircraft and things like that. So we just need a reaction. So hydrazine, you can look it up, but it's N2H4, and be like in a liquid phase. So I'm going to go ahead and put that there. All right, and then of course we've got it mixing with hydrogen peroxide. So we all know hydrogen peroxide is that that would. So we're going to take these two liquids, and they're going to be put together. When that happens, we're going to get some nitrogen gas, which is generated, and some water. Okay, and we're going to get some water. All right. So there's our reaction. I'll just put that there. Why not? So there's our reaction. So now from this, we know we need a balanced reaction. Well, we can see that we've got, you look at the hydrogens and you can see those are not very balanced. On the reactant side right now we have 6, and on the product side we have 2. We have 2 nitrogens on both sides, and that balances out. We have 2 oxygens on the reactant side, and then 1 oxygen on the product side. So, I don't know, my first instinct is just to go ahead and balance this over here so that there's, if I do this, I can see that I get 4 oxygens. And so now if I come over here and do this, I would have 4 oxygens. And what I saw ahead of time was I saw that if I had put a 2 here for 2 oxygens, that I'm going to end up having to make adjustments in some way for this and this because of the 4 right there. So what I did was, knowing that, I went ahead and said, okay, well, it looks like if those are already, the oxygens are already sort of doubled over here, made a call, I got 4 oxygens there. I can bring the oxygens automatically into balance. There's 8 hydrogen on the product side. So now I've got those 4 right there and those 4, so there's 8 on the reactant side. Everything is good to go. Okay, so now we're all balanced out. Now we can do some stoichiometry. Now we can do all this. So remember that the limiting reactant, we determine that by calculating, okay, the yield, right? The theoretical yield, but we want the one that is the least amount. So what that means is we pick a reactant. It doesn't matter which reactant you pick. You just pick a reactant. And then what you do is you do the math with that or you just pick a product, and then what you do is you calculate both of your reactants to that one product. So I misspoke a second ago. Pick a product, any product. It doesn't matter which product, just pick one. And then what you're going to do is you're going to determine from your calculations which one produces the least amount of product, and that one will always be your limiting reactant. And then of course the excess reactant is literally the other reactants that are there. All right, and then so the last part of this, where it says how much excess reactant remains, we'll take a look at that after we've established what the limiting reactant is and some of the dynamics that are occurring. Right, so in this we have 0.750 moles of hydrazine. So we've got 0.750 moles of hydrazine, right? Oops, I always do that. Of our N2H4, right? So it's in moles. So you can go to moles or grams and compare. So long as you're in the same unit, it really doesn't matter. So we would know we would need to bring moles of hydrazine down here. And so for every 1 mole of hydrazine, so you remember our coefficient, so there's a 1 here, right? You don't write the ones, they're understood. Let's just do all of our math to nitrogen, to the nitrogen gas. And the only reason why I'm picking that is because it's the first product that is here. That's the only reason I've picked it. No other reason. I could have picked water. Matter of fact, we'll use water for the second half of this problem just to change things up a bit, okay? So, and we can see here that in this reaction, 1 mole of hydrazine will yield 1 mole of the nitrogen gas. So you can see that unit cancels out, and when that does, we essentially have 0.750 moles over times 1 over 1, which is basically going to be 0.750 moles of N2. So now we want to do the exact same problem, but we want to do it this time with what we know we're given with the hydrogen peroxide, right? So that is 0.500 moles of the H2O2. All right, and in this reaction, we see that there are 2 moles of the peroxide for every 1 mole of the nitrogen gas. So we've got moles of peroxide to a ratio of moles of nitrogen gas. We can see there's 2 moles of these for every 1 mole of those. Cancel out our units. We should never forget to do that. And then half of 0.5 is 0.250 moles of N2. So knowing this is our least amount. 0.25 moles is less than 0.75 moles. We have the exact same unit, which is why we can compare the 2 numbers. So with this, that lets us know that the hydrogen peroxide, right, that the hydrogen peroxide equals our limiting reactant. And I'm just going to abbreviate limiting reactant LR just because I don't have a lot of room, right? So now we know that our N2H4, our hydrazine, that is our excess reactant. We know this for a fact. Okay, we have just now calculated it out. We could have calculated it out to grams of nitrogen gas and on both of these, and it would be different numbers than 0.75 and 0.25, but it would just be in grams, but it would still work itself out to where the limiting reactant was still the hydrogen peroxide. We just have it in gram units instead. All right, so we've got that right there. I'm going to erase all this just because I don't want it there. I want a clean slate. So, how about I do? We'll do the same thing. I'll show it to you, but we'll do it this time with water. All right. So we'll start out with what we originally had, which was 0.750 moles of the hydrazine. All right. And this time we're going to go from the hydrazine to water. So last time we did it to the nitrogen gas. This time we're doing it to the water. So I'm just going to show you that everything's still going to work itself out. All right. And I may have to erase this right here, right? Okay. Just to give myself some room. All right. So in the reaction, we can see that there's 1 mole of the hydrazine, all right, for every 4 moles of water. All right, we can see that. That unit cancels out. So now we bring the unit moles of water down. And so now we can go from moles of water to grams of water, and we know the molar mass of water is 18.02 grams. So that unit is gone. So now if we were to do the math in this we have 0.75 times 4 times 18.02 should see 54.06, and that would be grams of water. All right, so now we're going to take this right here, our 0.500 moles of hydrogen peroxide. All right, H2O2. And, excuse me, in the reaction we can see there's 2 moles of this for every 4 moles of the water, right? So we've got 2 moles of hydrogen peroxide for every 4 moles of water. Cross out the unit as soon as it crosses out. Do not leave that there. And so we bring down moles of water, and we're going to convert it to grams of water. And the molar mass, again, is 18.02 grams. Cross out our unit. So we do our math, and this actually works out pretty nicely, where if you think about it, we don't need a calculator for this, but you can punch it into a calculator if you want. So I'll let you hear me punch it into a calculator. 0.5 times 4 times 18.02, 36.04 divided by that 2 times 1 on the bottom divided by 2 gives us 18.02. Or you should have been able to see that 4 divided by 2 is 2, and half of 2 is 1, and 1 times 18.02 is 18.02. So a lot of times we can actually evaluate all of our work fairly quickly. It's just a matter of just seeing those ratios, those patterns. All right, so you see here again, we went to a different reactant, and this time I just did it all the way to the mass unit, grams, and you can still see that we get 18.02, 54.06. So this is still, we still recognize that the limiting reactant is the hydrogen peroxide, and the excess reactant is still the hydrazine. So the math still worked itself out well. Remember, I said it doesn't matter which one you go, which product you go to, you just have to be consistent, because you have to be able to compare the exact same unit every single time. All right. So now now that we've done that, let me get rid of all this. Let me make some room here. Oops. Let me see if I can clean this up for you just a little bit. I love this. I love this app. This is a great app. GoodNotes is a fantastic app. Fantastic app. All right. So last but not least on this, how much excess reactant remains? So the key part of this is knowing what our expected yield is. And so, we just finished doing the water, so let's just go with water. So our theoretical yield is 18.02 grams. All right. We know that that the hydrazine is our excess reactant. This we know. The question is, how much more is there? All right. How much excess reactant is there? Well, to answer that question, we first need to know how much do we actually use in this reaction. So we can go 18.02 grams of water. All right. Since that was the last example we used, I'm gonna do that. All right. So, and then we know the molar mass of water, and it just so happens that the ratios in this, the way that it works out, that 18.02 grams, that is the molar mass of water. So it just works itself out really, really nicely that we're going to get that number on the bottom. All right, that's the molar mass. It doesn't always work itself out this way, so don't think that this is always the case. It just so happened that it did. I didn't bother to change the numbers because I figured, it's a good learning exercise. All right, so we're going grams to mole. So we're going grams to mole, right? So we're going grams to mole, mole to mole, then mole to grams, right? So 18.02. So we're going to bring down moles of water to moles of the hydrazine. And we can see that there's 4 moles of water for every 1 mole of hydrazine in this reaction. Okay. Oops. Now, in 1 mole of hydrazine into H4, how many grams of into H4 are there? Well, if we do the math, we've got nitrogen is 14.01 times 2, all right, plus the 1.01 times 4, so that'd be plus 4.04, right? And that should give us 32.06. All right. Here we go. So now, if we multiply all that out together, we've got 32.06. So, well, if we can do some quick math here, 18.02 over 18.02 cancels itself out. So we really don't even need that. So we've got 32.06 divided by the 4 that's right here, right? Divided by the 4. That gives us 8.015 grams of hydrazine. All right. So now we could have stopped right here and just evaluated it this way, knowing that we have moles of hydrazine already given in the problem. Right here, we're told that 0.75 moles of hydrazine is initially added into this problem, right? So we can come back to this, and if we think about it just for a moment, all right, if we were to evaluate this part of the equation right here, well, that canceled that out. So we basically have 1 over 4. Well, that's 0.25, all right? Now, if you don't believe me, if that's confused you, then don't worry about it. We can just do our math over here. 8.015 grams of the hydrazine that we just calculated out. If you can't see that pattern, then you can just still work out your math, right? We know that there's 32.06 grams of the hydrazine, right, per mole. That's its molar mass. That goes away. Oops, I don't need to multiply it. We're just going to go to moles. So 8.015 divided by 32.06, you should see it says 0.25 in the calculator. And since we started out with 3 significant digits with 0.750 and 0.500, I'm just going to go ahead and add a 0 right here to be consistent. So this is how much is needed. That's what we just calculated, was how much is needed. Now, if you think about it, originally, so how much excess? Well, we originally had 0.750 moles that was added in. Well, if we subtract out how much we actually need, this makes sense. I don't care if you're talking about chemistry units or if you're talking about your baking cookies. If you know you have an excess amount, you just subtract out what you use, whatever's left over, that's your excess. So you should easily be able to see this is 0.500 moles. And of course, this is our excess reactant, so we know that this is the hydrazine. So that's the answer to the last question. If we wanted to figure out the excess in grams, we would just convert this 0.5 using dimensional analysis, and we would get the mass of it, right? So that's it. Remember what you do. Let me clear all this for you. And summarize this lesson. And again, definitely rewatch this thing. Definitely do that. Take notes. So, limiting reactant. that's always going to equal the theoretical yield that is less, and that is in mass or mole units. Doesn't matter. Typically we go to the mass unit because in lab your scale doesn't measure out moles, it measures out a mass unit, measures out in grams, right? So typically we just go all the way to mass. And on your assessments, unless otherwise asked for, that's usually what I'll assess you on is mass units, because that's practical. It's what we do in class, right? The excess reactant would then be the other reactants, because all of those would be higher. So it's either going to be one reactant or could be more than one reactant. Every once in a while you run into something where you have three things that come together, and these very complex reactions. Typically we'll just work with two. All right. And then from here, how much excess reactant? Well, if you think about it, if you know how much is needed, then just take the difference of how much is needed from how much is used. So if you think about it, it becomes a very simple math problem. How much added or used minus how much is needed. And that's going to give you your total amount of excess reactant. So you just have to make sure that you're in, if you either subtract moles from moles or grams from grams. Either way, it gets you the correct answer. If you do it moles, then you just have to convert it to grams, and it'll still be the same thing. And then you just always pay attention to your significant digits. Hope that helped, and definitely rewind, rewatch, take notes. Work on those practice problems. As always, the answers for those solutions will be posted. Always good learning with you. I will see you in another video really, really soon.